Today, we're going to look at the law of conservation of energy as applied to cosmology. If you look at the book by Paul Dirac on the general theory of relativity, you'll see that on page 45, he says, in curved space, the conservation of energy and momentum is only approximate. Now, for cosmology, we need a 100% accurate definition of total energy to apply the conservation of energy law. The Big Bang Theory is being cast into doubt by observations, particularly the brilliant observations from the James Webb Space Telescope, which show galaxies in the far distance, which must have formed more than 13.8 billion years ago. So the Big Bang Theory is in serious doubt, and one of the key issues with the Big Bang Theory is that it violates the law of conservation of energy. The Big Bang Theory says that all the galaxies that we observe in the universe, if you go back in time, they get hotter and hotter, and the universe gets denser and denser. But ultimately, when you get back, there is no explanation for the source of energy for the matter formation. So what we're going to look for is a cosmology in which matter formation doesn't take place right at the beginning, but takes place progressively over an extended period of time. So our starting assumptions are that the source of energy for matter formation in the universe is the expansion of curved space. And we'll look towards the end of the talk at verifying this hypothesis in terms of our fundamental equations of the universe. So we're going to make the assumption that the expansion of space is uniform over time and distance. And this assumption may seem to contradict the current thinking that the expansion of the universe is accelerating, but that's not the case, and there's a different explanation for dark energy, which will be explained in a later talk. So we start with the assumption that the expansion of space is uniform over time and distance. So the Hubble constant that we see, we can observe today, is the same which would be applied in the past and over greater and greater distances for space itself. So let's look at, at the expansion of space. And in this diagram, we have a distance s. And over time, after a time delta t, that distance s expands by an amount delta s. And the statement that the expansion is uniform breaks down to the point that delta s depends on the length of s and also the time. And this constant k is the constant of proportionality. And in this analysis, we measure s in light years, t in years, and k is a constant in units of light years per year per light year. So that's speed per distance. And this is, in fact, the Hubble constant. And the reason why I haven't shown it as h naught is because h naught is usually expressed in kilometers per second per megaparsec. So we can use calculus to work out the relationship between s and t. So we start with the expression delta s equals ks delta t, and we rewrite that as ds by dt equals ks. So we bring the s over to the other side and we get integral 1 over s ds equals integral k dt. So integral 1 over s is log, so log s equals kt plus the constant of integration. And we can use our initial starting values, t naught and s naught, to derive the expression s equals s naught e to the k t minus t naught. So looking at this expression, the value of k, we can look at the observation horizon, which is at 14 billion light years. And what that means is that when s is 14 billion light years, the recession velocity ds by dt is the speed of light. And in our units, the speed of light is 1. And so from this expression, 1 equals k times 14 billion. So k must be equal to 1 over 14 billion light years per year per light year. And you can convert these speed and distance units into 69.84 kilometers per second per megaparsec, which is within the range of possible observed values of the Hubble constant. So from this, we deduce the fact that the universe is expanding, and every length segment expands by a factor e, which is approximately 2.71828 every 14 billion years. So that implies that the radius of the universe increases by that amount, by e, every 14 billion years. And the volume of the universe increases by a factor of e cubed, which is just around 20. Now, when we look at general relativity, we have this fundamental equation of the universe, which relates energy momentum to space curvature. And what we have to do is to take on board this fundamental equation and modify our definition of total energy to include space curvature. And then we have an exact and precise total energy in which we can apply the conservation of energy law for the universe as a whole. Now, mass and energy are always positive, and so the energy of space curvature must be negative in this equation. And the total energy of the universe is always 0. So you can see from this analysis that there is the potential of deriving matter in the form of mass from changes in space curvature. So here's an illustration of the curved space expanding. So you can see that in the radial direction from the center, the universe is flat. So when we look out towards the distance, we see flat space, but space is curved in the direction parallel to the boundary. And as this expands, the radius of curvature increases. So this implies a change in space curvature, which has the potential to release energy for matter formation. And you can see that in this context, the radius of curvature is smallest close to the center. So any matter formation we would expect to be greatest close to the center of the universe. So from this, we can conclude that the universe is finite with a space boundary, because this release of energy hypothesis wouldn't work if you were in an infinite universe or if you were in a finite universe with no boundary. The radius of the universe increases by a factor of around 2.7 every 14 billion years. And the volume of the universe increases by a factor of 20 every 14 billion years. So if we assume that the formation of galaxies is proportional to the volume of the universe, then the number of galaxies itself increases by a factor of 20 every 14 billion years.